Hello, friends. This is a video on how to combine electric fields from multiple charges, and it's what we've been doing this week in class. Um, so if you've missed class, this is perfect, or if you just need a review, this is perfect. I'll start by doing simple drawings. I'm going to move relatively quickly, so feel free to pause, per usual, rewind. If I have a dipole of charges, a dipole is where you have an equal positive and negative charge separated by some distance. We're going to analyze different points in space. So a point in space here at point A, we'll call that a distance d from each charge. And we'll just analyze point B and point C separately, not doing the algebra just to save time. The electric field at point A, the first step you do is draw E1 and E2. And if we do multiple, say I do a third charge as a source charge, you do E3, E4, etc. And then you add them up. Add them as vectors. And this gives you E total. This is a principle called superposition, which basically says the electric field here is simply the vector sum of the charge 1 and charge 2 field. You just add it up. So it's another way of saying it, it's easy. Right? So if I draw the electric field from 1, remember, E field is out of positive and into negative. This is creating the field. Remember, this is creating the field. We're not feeling the field yet. There's no test charge here yet, although you do want to pretend that there's a positive test charge here. It gets repelled by this, and it gets attracted to this. So they don't subtract, they add. They're in the same direction. And so we get E1 plus E2 to the right. If you want to create a vector direction where positive is right, then you just say both of these are positive, and you give a positive E1 plus E2, and then your result is positive to the right. Either way, I get what? KQ over D squared, because D is the distance, plus KQ over D squared. So that gives me 2KQ over D squared, right? If we give you numbers, you plug in numbers. If it's letters, you plug in letters. Either way, this is what you do. And this is the general solution. At point B, what happens is charge 1 creates a field pointing away, E1, which is the same value as here because it's the same. We'll call this D, actually, might as well. But charge 2 is now smaller. Here, charge 2 creates a field that is a ninth E1. Why? Because it's 3D away compared to D. It's 3 times farther. We'll say R is times 3, therefore field is times a ninth. So the total field here, E at B, is, well, we can call, let's do vector directions for this one. E2 is positive, E1 is negative. So we do a negative E1 plus E2. So here we have negative KQ over D squared plus KQ over 3D, because that's the distance. 1, 2, 3D squared equals negative 1 plus a ninth. Careful, you have to square the 3. Gives you negative 8KQ over 9D squared. I'll let you look at that algebra more closely, confirm this is what you get. The negative, though, means what? It means left. So you could have just said this one's bigger, so left wins. So therefore, I know that this is left because this is bigger. Left wins. Right? Therefore, the answer is left. And you can do the same reasoning over here. I'll just do the reasoning. At point C, the field from charge 2 is toward because it's inward. Pause. Realize that at charge 2, it's inward again. rewind this to follow my logic, every step requires a thought applying these concepts, and this is really important. Step one is this points inward, charge one points outward, or creates a field that points outward, sorry. Therefore, E2 wins, and we have a total field that here points to the left. So EC is left as well. EB is left. Great. So if we want to, so pause that if you need to, but if we want to draw the entire dipole field, it's going to point this way between the two charges. What we actually will get is that it's a minimum in the middle. It's bigger here and smaller here. Here I would have E2 be here, E1 be here. They're adding up to this. Here we have, sorry, E1, E2 is bigger. Here E2 is bigger because it's closer to 2. Here E1 is bigger because it's closer to 1. And then E1 is farther away, but they add up. Here they match, but they're farther away from each other. So here's a minimum, it's maximum. We can graph this eventually. In fact, if we wanted to graph this, what we would do is say, all right, here's a point X, that this is a distance X from here, and that this distance we'll call total. I know I called it 2D before, but let's call it just D right now. That means this is what? This is D minus X. Therefore, the electric field at our general point X, E total is going to be what? It's going to be KQ over X squared plus KQ over D minus X squared. Careful, this is not the same that's in the homework because the homework has two positive charges. This is a positive and negative. This is a dipole. If you graph this, it looks something like this. This is at D over 2, right in the middle. Kind of cool, right? Right, that's at D over 2 right in the middle. This is D, where it asymptotes to infinity. Why does it asymptote to infinity? Because you're now infinitely close to this charge, and it's a 1 over r squared function, so it just goes to infinity on both sides. That's pretty cool. The rest of it looks like this. It goes left here, and if we graph the entire thing, pause that. That was important, but I'm moving on. It goes straight to the right in the middle. Here it goes like that. When you're directly above and below, it points straight to the right, because if I go straight out from charge 1, boom, and then straight into charge 2, boom, that tailed ahead gives me a vector that's directly to the right. Same with up here. I go straight out of charge 1, straight into charge 2. That gives me a vector to the right. The components in the vertical direction cancel. If you want to look at it as components, it all works out. And again, I'm just going to go a little quickly just to show you the total concept. This is what we're doing for those of you who missed it. All right. The rest of it, if you fill it in, looks like this. It goes left here, comes out like this, but it curves back. When I say it curves, what I mean is if I draw an arrow at every point, it's straight, but the arrows, as they progress, seem to curve. So when I draw the curve line, it's actually a bunch of little arrows together. Straight above, it gets weaker. Straight below, it gets weaker, but it's directly to the right. Here, it's also inward toward the negative. So it goes out of the positive into the negative. This is the dipole field. It's the same as a dipole magnetic field. If you've ever seen a magnet, this is the field from a magnet. Same with a dipole electric charge. There it is. Adding the vectors E1 and E2, obviously using the equation KQ over R squared for their magnitude. The direction is out of positive into negative, right? That's what we're using. We're using these concepts, right? And applying it to the situation. So what if we apply it to the a situation of two positive source charges? Well, in the middle, what will happen is out of 1, out of 2. Out of 1, out of 2. Confirm this drawing, make sure that makes sense to you. So the E field in the middle is actually 0 because it's KQ, we'll say this one's negative. KQ over D squared minus KQ over D squared. That's 0. Awesome, so we actually have 0 here. Here it's gonna go out of 1, out of 2. The vertical component, sorry, the horizontal components cancel and we get a net vertical component upward here. Here we get the same thing, but downward. Here it goes out of 1, out of 2. So the total here, this is E1, E2, E total points left. Here we have E2, E1. Pop quiz, why is E1 smaller? Pause the video. Why is E1 smaller? Because it's farther away. Why is E2 smaller? Pause it. Why is E2 smaller? Pause it. Think about it. Because it's farther away. But I still add them because they're in the same direction. I still add them because they're in the same direction. So E total here points out, points out. If I do one here, I go out of 1, out of 2. Sorry, out of 1 will be smaller than 2 because it's farther from 1 than 2. So the total points kind of up here. What about here? Out of 1, out of 2. So it kind of points up like this. Here I go out of 1, out of 2. So it kind of points up like this. So we end up getting these arrows that kind of curve up this way. They kind of go like this, kind of like this. Notice here is interesting. It's out of 1, but out of 2. Now they go against each other. So here we would subtract, right? Here we subtract this one minus this one, and we actually get a net vector to the right. E total here is to the right. E total here is to the left. So it's just out, right? It's just going out, but here it kind of curves down into the vertical, right? Curves like this way. Again, it's not actually curving. What it is just a bunch of straight arrows that if I put them in a row, they would appear to curve like this. They would get more and more vertical. Like here, it would go like this, and then like this, and then like this. A bunch of straight arrows in a row that if you look at them really close together, they appear to make a curved line. So the electric field here goes like this. The electric field here goes like this, right? And here's our, what do you call this? Two positive pole? That's a weird word. There's got to be a word for this one. Two positive charges creates this type of field. Kind of goes like this. There you go. That's how you add it. So on the homework, question 1 is where I have 2 protons. Careful, a proton has a charge E, right? Positive. And therefore, instead of Q, you're just going to write E. So don't make it hard. Don't overthink it. And you're going to set up a thing where you have a general point X here. And so the distance from this is X. The distance from this will be D minus X. And so you end up getting an electric field that you can map. Now, you're going to then plug it into Desmos and do proper, I tell you exactly what window to plug in, but I'm going to show you what it looks like on Desmos right now. So here I plugged it into Desmos, right? So this is what you should get. If you plug in E into Desmos, E is the numerical E, 2.73 something, something, something that's used in calculus. So you can't plug in E electron into Desmos. It's not a physics calculator, it's a math calculator. So you have to plug in Q and then make Q the charge of a proton, which is the same as the charge of an electron. So don't get confused about that. Remember, they have the same charge. Here's the formula. It only works between 0 and D. D was 10 to the negative 10. K is 9 times 10 to the 9. I like doing constants. It makes it look cool, nice. It makes it look cool, nice. Makes it look cool, right? Makes it look nice. And then you just put in Desmos, what do you want those constants to be? And it should look like this. Where is it positive? What does that mean? Where is it negative? What does that mean? This is a vector. It's easy once we look at it. And what's the shape of it and why does it make sense? Once you look at it, it's actually pretty obvious, but I think it's fun to plug it into Desmos. We're going to do a little bit more of that and see what you get. That's it. I invite you guys to do the bonus where you do the 2 positive charges. Gosh, I think I have that in there. I hope I do. Where you do the vertical field E of Y. It's kind of a fun one to do. Either way, that's my video. See you guys in class.